Welcome, everyone. Today, we're diving into the fascinating world of linear time invariant sampled data controlled systems. These systems form a crucial part of modern control theory and are instrumental in various engineering disciplines. We'll explore how these systems work, their components, and their applications in technology and industry. The heart of such systems is the sampling period, denoted as T, which determines how frequently we sample our output and how often the digital control sends the command input. This process involves digital to analog converters, DAC, and analog to digital converters, ADC. We'll explore how the command input varies in discrete U of k and continuous U forms, as well as the measured output represented as Y of k for discrete and Y for continuous systems. This sets the stage for understanding how digital controllers interact with physical, continuous time plants, including sensors and actuators. Now, let's delve into the continuous representation of our systems. In this context, we explore the mathematical models that describe the system's dynamics. These equations typically do not provide the precise mathematical descriptions of the physical plant, covering every possible state of the system. Instead, they offer models that aid in the analysis and prediction of system behaviors around desired states. We introduce the mapping matrices A subscript C, B subscript C, and C subscript C, which represent various system matrices in continuous time. Now let's shift our focus to K equals A subscript Cx plus B subscript Cu. This equation delineates how a system's state evolves continuously over time, akin to watching the gears and levers of a machine move seamlessly. Similarly, Y subscript C equals C subscript Cx illustrates how the system's output relates to its internal state in the continuous world, capturing the essence of its functioning. However, here's the twist. Real-world scenarios often require us to work with discrete time, necessitating the sampling of the system's behavior at regular intervals. This is where the discretization process comes into play. It's like converting those smoothly moving gears into precise ticking motions, much like a clock. The transformation involves matrices A, B, and C. One common approach to discretize the A matrix is by using the formula A equals E A subscript CT, where T represents the sampling period. Now envision having a continuous system operating seamlessly, and your goal is to comprehend and control it within a digital realm. Through discretization, you break it down step by step, much like frames in a movie. The matrices A, B, and C become your trusted tools in facilitating this transition. A discrete sampled data system could be a robot, an aircraft, or even a financial model. To understand and control such systems, we need a way to describe how they behave. Discretization is like capturing snapshots of the system's state at regular intervals and then using those snapshots to predict what happens next. In the viewed representation, you have two key equations. First, x of k plus 1 equals a times x of k plus b times u of k. This equation tells us how the system's state at time k plus 1 is influenced by its state at time k and the input at time k. Second, y of k equals c of k. This equation reveals the system's output at time k, purely based on its internal state at that moment. The transition from the continuous time equation to the discrete time equation occurs because the system is sampled at regular time intervals of t. This means you observe the system's state and output only at the time instances kt. Let's explore why we need these representations and how they benefit us. Understanding the system. A representation serves as a mathematical model that helps us comprehend the behavior of complex systems. It's like having a map before embarking on a journey. Without a representation, we'd be navigating blindly, but with it, we gain insights into how the system responds to inputs and changes over time. Monitoring the output. Representations allow us to predict and monitor the system's output or response. This is crucial for various applications, such as quality control in manufacturing, tracking the performance of a spacecraft, or predicting the behavior of financial markets. It's like having a dashboard in your car that shows your speed, fuel level, and other essential information. Designing observers. Observers are mathematical algorithms that estimate the internal states of a system based on its inputs and outputs. In cases where we can't directly measure the internal states, representations help us design these observers. It's akin to having sensors and instruments that can tell you what's happening inside a machine, even if you can't see it directly. Control design. To control a system effectively, we need to understand how it responds to different inputs and how changes in its internal state affect its behavior. Representations provide the foundation for designing controllers that can regulate the system's performance. It's like having the steering wheel and pedals in a car to navigate and control your journey. The transition from the time domain to the frequency domain represents a fundamental mathematical transformation in the analysis of dynamic systems. It involves a substitution of the discrete time index k with the complex variable z, introducing a complex perspective that enables the examination of system behavior in terms of frequencies. The first equation encapsulates the evolution of the system's state, accounting for the influence of complex frequencies represented by z. The expression z times I minus a to the power of minus 1 serves as a frequency domain transfer function, analogous to the Laplace transform in continuous time systems, providing insights into the system's frequency response. Y of z equals c times x of z. This equation expresses the system's output in the frequency domain, relating it to the complex state representation, thus allowing us to understand how the system interacts with different frequency components. For stability, we use mathematical tools like eigenvalues, Nyquist plots, and Bode plots to determine if the system is stable. In simple terms, we're looking for signs that the boat won't capsize, ensuring smooth sailing through various conditions. For controllability, we investigate whether we can reach any desired state, starting from any initial condition. It's like checking if you can navigate your car to any destination from any starting point with the right set of controls. For observability, we determine if we can reconstruct the complete picture of the system's internal states from what we can observe externally. Think of it as ensuring you have all the puzzle pieces to see the entire picture, no matter how complex. Furthermore, frequency domain analysis facilitates the design of control and observer systems. By leveraging frequency-based techniques like loop shaping and pole placement, we can engineer controllers and observers that shape the system's response to meet specific performance criteria. Get ready for what's coming next. We're about to dive deeper into the fascinating world of internal stability, controllability, and observability. These topics are the hidden gems in the realm of sampled data-controlled systems. Stay tuned for our next session as we promise to unravel the mysteries and provide a comprehensive understanding of these critical areas in control systems. It's going to be an exciting journey of exploration and analysis. Don't forget to like and subscribe.